Okay, this is example 1 from 1.1 in Math 20-1, and it's just talking about a sequence. It says that the person will be paid $12 for the first hour, 19 for the second hour, or 19 for 2 hours of work, sorry, 26 for 3 hours of work, and so on. Now, when we talk about general term, this is Tn, and in this case, n would be equal to the number of hours worked. So the best thing I think to do is to start with what the sequence actually is. So the amount of money that this person could get paid is $12 for 1 hour of work, $19 for 2 hours of work, 26 for 3 hours of work, and then this pattern is going to continue. Now, I mean, technically this could be described as an infinite sequence, but I'm sure, you take the average lifespan and that's going to be the highest hours of work that you could possibly work, although nobody's going to work their entire life. So to write the general term, what we have to do is we have to look for that formula on our formula sheet, which I'm writing in place. And what students struggle with is the idea that if we're finding the general term, I don't know what n is yet. And it's a good thing, I think, conceptually to understand that Tn depends on the value of n. And it really does make a function, an equation, like several of the ones we've looked at throughout the year, that the value Tn depends on n. And I want to put this in function notation that I could write this, that Tn as a function of n is equal to term 1 plus n minus 1 times d. The only difference is that the n value in this context actually has to be a natural number. And the natural numbers are 1, 2, 3, 4, and so on. So n can't be 0. There's no 0th term. There's no negative terms. We're only going to look at term 1, term 2, term 3, term 4. I mean, term 10 billion. 10 billion is a natural number. That's okay. Now, in order to do this, keep in mind that Tn is our general term. N is, and I'll put that underneath, well, I already wrote it. I'm not going to write it again. N is the number of hours worked, and I'm going to put underneath it that Tn is the amount of money we make for working n hours. I think it's always good to identify what our variables are. So as long as we can figure out term 1 and the common difference, we're good to go. We can plug those into the equation. So without further ado, term 1 is the first term, which is 12. Now the common difference, I want to write it that we could do term 3 minus term 2, or I could do term 2 minus term 1, or the general formula for it is the common difference is any term subtracted the term before it. And then in this particular case, n would not be able to be 0, right? There's no 0th term. So what I'm going to say is that my general term is going to be the first term, which is 12, plus whatever n will be, minus 1 times the common difference. Now, the common difference is either 26 minus 19, which is 7, or 19 minus 12, which is 7. At least initially, I would recommend that you make sure that that common difference is very, very consistent throughout the question, because it needs to be. If I got, 26 minus 19 was 8 and 19 minus 12 was 6, that's not a common difference. That's just a random sequence of numbers that we've written out. So arithmetic sequences are very, very consistent, and the common difference is always how we get to the next term in our sequence. So I'm going to put in a bracket here the common difference, which is 7. Now, personally, I like to expand and simplify that formula. So I'm going to say that Tn is equal to 12 plus 7n minus 7. And now I can say that the general term of the sequence is 7n plus 5. Now, really what this means, if we wanted to attach kind of a logical meaning behind that, is every time we make n go up by 1, we're adding 7. So that's our hourly rate. We're getting paid $7 an hour. But for whatever reason, if I come in for an hour of work, I get paid the $7, but I get paid an additional $5 just once. So maybe that's, a drive to work fee. Maybe that's the minimum amount they pay. I don't know. Not a lot of us probably have jobs like that. But that 5 is just there because the first term isn't, 7 when n is equal to 1. It's 12, which is 7 plus 5. Now, B wants us to figure out, and I'm going to write this, they want us to figure out 6 hours of work. If n is equal to 6, then what we are finding is the 6th term. And that's really important. That's not t times 6. That's t with what we call a subscript 6. And that's just there to give a little bit of a deeper meaning behind the actual algebra that we're going to write out. And what we can say is that term 6 is equal to 7 times 6 plus 5. Really important that these n's have to be the same value. You cannot find the 6th term by putting 40 in for n. That's just nonsensical. And then what we would do at this point is we would simplify. So term 6 is going to be 42 plus 5. So you would get paid $47 for 6 hours of work. All right, I think I'm going to lump two examples into each other because they're really not too bad in this section. I went the wrong way. Sorry about that. So the second example here, when I get to it, is talking about muskox in northern Canada. It says in 1955, the muskox population was 9,250. Suppose that in subsequent years, the growth was an arithmetic sequence in which the number of muskox increased by 1,650. All right, so what that means, and I'm going to put it up here, that 1955 is the first year, and this is going to carry on to some other year past. But what that does mean is that we are going to make the number of bison in 1955 9,250. Now, here's the problem with doing this, and there's nothing wrong with it, that if we make that 9,205, then the first term is how many bison there were in 1955. The second term would be how many bison there are a year later. The third term would be how many there are 2 years later. And we start to get a little bit of a disconnect between the term number and how many years have passed. So what I would recommend that you guys do is actually look at how many there would be in 1956. And what I'm going to do is I'm going to add that 1650. And if I take 9,250 and I add 1650, I get that there's 10,900. Now, the advantage to this is if I make this n is equal to 1, then 1 year has passed. And we start to see a bit of a better connection between our n value and how many years it's been since the bison population was getting bigger and bigger and bigger. So this was a useful means to an end, but I'm not actually going to make that a part of my sequence, because now when n is equal to 1, it's been 1 year. When n is equal to 2, it's been 2 years. When n is equal to 530, it's been 530 years. And that makes doing the math a lot easier. That being said, we do still have to find the next term. So I'm going to add 1650 again. And I get in 1957, or 2 years after these bison have been allowed to repopulate, I have 12,550 of the animals. And I'm going to do one more. If I let another year go by, what I have is 14,200. And what's going to happen is that this pattern is going to continue until we get to either 100,000 or a number bigger than 100,000. Now, in order to solve this, what we have to do is come up with our general term and then put 100,000 in for it. So I'm going to say that Tn, which is term 1 plus n minus 1 times the common difference, that means that Tn is equal to 10,900 plus, we don't know n yet, so we're going to leave it as is, and then the common difference was the 1650. Now again, I think it's better to simplify this. So I'm going to say that Tn is 10,900 plus 1,650n minus 1,650. And what I get is that Tn is equal to 9250 plus 1650n. And we see that 9250 show up again, but it's not in the form on your formula sheet. 9,250 is not the first term. It's just what we're adding that 1650 per year onto. So what the question is really asking is, what does n have to be so that Tn is greater than 100,000? Now, the reason I put that inequality in there is we might find that at the end of 1 year, it's 99,999, and then the next year it's 101,000. That's okay. We're just looking for the point where it's going to reach and eclipse or get bigger than that 100,000. So what I'm going to do is I am just going to solve for when it occurs. So I'm going to put 100,000 in for my Tn, and then I'm going to manipulate this equation to solve for n. And the way that we do that is we subtract the 9,250. And what I get, I'm just going to grab my calculator and make sure I don't make a mistake here. When I do subtract that, I get 90,750 is equal to 1650n. So I'm going to divide by 1650. And when I do that, it's nice of them to do that, then we get 55 is equal to n. So 55 years until our bison population gets to 100,000. And it actually got to 100,000 directly. If I got like 54.943, I would just round that up to 55. N has to be a natural number, so don't try to tell us it's 40.6 or pi or any of those non-natural numbers. Okay, that's examples 1 and 2.